is to tell you how I end up calling Kristen Abu Ayman. One time during the math fest, there was a student. I think he won or something. So he came to my office and he said, you know, I told him what? He said, it seems Ayman is a good person. So I told him, okay, I'm going to call you Abu Ayman. So basically question that is in number theory, and in I cannot claim that Paul Erdős started that. If you read, you will discover that somebody else discovered that, but definitely Paul Erdős, he is the one. I mean, he worked a lot on this problem, which called the Ramsey number. So let's understand what we mean with the Ramsey number first in general. Let's.
Ayman, are you sharing anything with us? I'm not seeing the.
Oh, I'm sorry. I will share that with you in a minute. It's my fault.
Okay.
And K4 and so on. These are in a graph theory. So what I will be talking about, the following. Here is the question. Find smallest positive integer k. I want to find the smallest positive integer k where 4 Ramsey number 5, 3. What do I mean? I want to find the smallest positive integer k for the Ramsey number 5, 3. I want to explain it, as I told you, not in a graph. I want to explain it in unofficial language or street language. Imagine you went to a conference and you want to know what will be the smallest number of participant, that's k, where for sure you know there are 5 persons, they know each other, or there are 3 persons, none of them know each other. So I want to know what is the smallest number. I mean, random, like you're going to a gathering, you don't know who is there. But I want to guess a number, k. What is the smallest positive integer k, where I could have at least 5, where each, I mean, they know each other. What I mean, they know each other, like, you know, this person, know this person, know this person. They know each other, all of them. I mean, like they are each 2. Is that clear? Or there are 3 persons, like that. There is nothing there. They do not each other, like this person does not know this person. This person does not know this person, and so on. This is what we mean with the Ramsey number for a graph in general. And that's due to, you know, I really don't know the first person who invented that, but I know that was one of the problems that Paul Erdős worked on, and he contributed to this theory, Ramsey number. Please, if you don't, because look, I don't want to waste your time here. I'm here to have fun for 40, 50 minutes. So is the problem clear? If not, I repeat, because I see there are some students. Yeah? Shall I continue? Okay. All right. Clear. Very good. Thank you. So let me ask the same question, but remove R. We're gonna have R because the numbers I know, like R3, 3. What is R3, 3? I want to know the smallest positive integer k. I mean, how many should be in the group so that at least a 3 person every 2 know each other, or there are 3 persons, none of them know the other out of the 3. So you will have 3 persons like that. This person know this person, this person, this person, or you will have that. It turns out R33 is known, this number, which is not difficult, 6. So if you go to a group and you know in this group there are 6 people there, then your statement will be correct. What is statement? A statement that we will have at least 3 persons where every 2 know each other, or there are 3 persons where, you know, they don't know each other. I mean, every 2. Okay, anyway, to make it short, what about you're gonna, the same question, you're gonna ask me, what do I know about, cancel, okay. What about the number R, let's see, 6, 5. Again, what do I mean R 6, 5? You think of, I want to know the smallest positive integer k, and here I'm talking about like how many persons in the group. K will represent how many are there, where you will have 6 people, and of course here, you know, I'm an Arab, and you know, my people and and you know, the P and the B, you know, that's okay. He's laughing. Okay. Because my kids always ask me to keep repeating, you know, like people and you know, and book, and I don't know what the hell they're talking about. Anyway, so 6, 5 mean, I want to know the smallest positive integer, how many in the group. So I will have 6 person, that's a good one, where every 2, they know each other, or there are 5, at least 5, where they don't know each other. And you're gonna now scream. Why? Till this minute, the only thing we know that the number is between 58 and 87. The minimum number k has to be, we don't know, but we know it's between 58 and 87. And this is like, you say, wow, seems like a trivial question. How come, you know, still unknown? In fact, the known numbers, to my knowledge, maybe up to 3, 9. We have a complete answer for R 3, 9. R39 is known, this number, which is 36. So if you have a 36 individual in a group, then your statement will be correct. There is at least 3 persons where they know each other, or there is at least 9 like that. They don't know each other. Okay? And of course, remember that the selection is random. You don't know I mean, like, you're going to a conference. If you have that many individual in the conference, this statement will be, okay, now you're gonna tell me, well, what about 35? Remember, this is the smallest, and that's the beauty. So that means 35 will not work. Maybe it will work for some cases, if you know that, I mean, but we're talking about random, and be careful here. So, like, okay. So this problem here, what I have here, imagine you're gonna scream again that R10, 10, the smallest is a number between 798 and 23,556. This is still an, with all these machine we have and fancy, this number is still not confirmed. R1010 is a number between 798 and 23,556. Isn't it that amazing? I mean, when I look at the problem at the beginning, as you know, I'm not a graph theorist, but when I saw that, I am one of the naive, I was so naive, I thought I can give this question to an undergraduate. I thought it's easy problem. But man, this is not the easy problem at all. I mean, and this is what the last thing I look at, 1010. Yeah, I mean, sometimes, you think the problem is easy, but it's not. Okay, so let me get to what I want to talk about. Let me change this question. And this has to do with the partial order, because a graph, and that's our talk, but I gave you here introduction. Here is what a question I have. Like, in a classroom, what is the minimum number of students in a classroom? Oh, damn, it happens all the time with me. Yeah. The minimum number of students in a classroom, let's call it K, okay, where I need Ramsey number. Now I'm going to define it in a different way. Look at what my, if you want, you can do R and index by P for partial order. Why? This is math. I'm not going to, as I told you, I'm not going to talk about math. But what's interesting is like the number here, like 3, 5. What does it mean? I mean here, I mean, I want at least 3 students, okay? At least 3 students where the age of A1, let's see that we have 3 students, let's give them a name, A1, A2, A3, where the age of A1 is less than, strictly less than the age of A2, strictly than age A3, or I have 5 students or 5 students where the age, let's call them B1 up to B5, where the age of B1 equal age B2 equal the age of B5. Keep going. All right, so now here, when we talk about this thing here, this has to do with partial order things that, you know, maybe in my graph theory, I will add this section and I will teach you about, it's not difficult. You only need to know what partial order relation, and I will get to it. But let's, I mean, here, as I told you, my goal is to amuse you and, you know, have fun. That's the goal of my talk, not much math. This is kind of interesting question. Like how many, what is the minimum number of students where this statement will be correct? What is correct? That I need at least 3 students, I give them the name A1, A2, A3, where the age of A1 less than the age of A2, less than the age of A3, or 5 students where the age of the first is the age of the second till I reach the age of the 5th one. Okay, for this kind of a question, we have a complete answer. What I'm trying to tell you, like here, I can tell you the minimum number of K here, I can guess, not guess, we have a proof for that, like 9. If you, this is the minimum number you should have in order to make this statement correct. And remember that we don't know the student. I mean, like you enter a room, you don't know who the hell is sitting there. Okay? And you want to make a statement like that. Like, I want at least 3 students where this is true, or 5 students where the second one is true. Okay? The minimum number of students should be 9. If you have 8 students, this statement could be wrong. And maybe I can give you a minute or 2 minutes, maybe a good student here can tell me that number 8 will not work. Like you can maybe, let's construct where this cannot be right. Like you could have with 8 students, let's see. Like I can have 15. Well, let's have a reasonable age, like 20, 20, 20, 20, and then like 21, 21, 21, 21. Okay? And remember, the relation here is strictly. So if you have you could have a classroom with 8 students, and these are the ages, right? So this statement is not correct, clearly. You cannot, out of these 8, you cannot find 3 where the age of the first less than the age of the second, less than the age of the third. And definitely you cannot find 5 students where the age of the first equal the age of the second equal, and so on.
Ayman,
You cannot.
can I ask a question?
Yes.
So here the age supposed to be defined in years, correct? If you change it into days, it will be different, correct?
No. Years.
Years. Okay.
I mean, I don't care. I don't care. I mean, we know what. Yeah, in years. I'm talking about years here.
Yeah. The second question.
Not.
Yeah. So here. Yeah. So here you have you have a graph, and you are adding weights to the edges, correct?
Not really. I'm doing a partial order.
Okay. Okay, thank you.
That's, yeah, I'm doing partial order. Like if you want to know what I'm doing a graph. First thing, I should have a partial order relation. You can define a partial order relation on 9 students. How? Each student, the age of each student equal to itself. And, you know, if the age of A less than the age of B, strictly less, then definitely the age of B is not less than the age of A. So we have the second axiom. You know, so this relation is a partial order relation on a on 9 person. Okay.
Okay.
In fact, yeah, yeah. As I told you, Ziad, my goal in this talk is just like, you know, common language. Usually when you ask somebody how old are you, they tell you 19, 18, 17. That's I'm doing it exactly like, you know, practical things. Okay, now let's ask the same question. Remember that in the original question, where the original question I was talking about earlier, there was a graph in general. Here, the problem is different. I'm constructing a graph from partial order. So to make it short, like ask me the same question and choose any 2 numbers. Anybody want to give me what is n and m? Give me 2 numbers. Anybody? Randomly. Make them as big as you want, like 20 and what? 11. Or let's make it 21 so I know how to add and multiply. So what is the question now for this kind of setting? What is the smallest number of students in a classroom? The smallest number of, so when you enter, you will if you say this statement will be correct. What is the statement? There are at least 21 students, where the age of A1 strictly less than the age of A2, keep going, strictly than the age of student 21, or there are at least 11 students where the age of B1, student 1 equal, keep going, age B11. And I should have the minimum number. What is the minimum number? The minimum number here, I can tell you, maybe it surprise you, or maybe not, which gonna be 201. We should have, and remember what that means. And that's what really I get excited. I mean, I don't know. People get excited for different reason. But I mean, this thing here, it means 200. If I choose 200, I can construct an example where this is wrong. The minimum number for this to be true is 201. Okay? And you can, I know some of you like Abdul, I know, and I don't, let me look at the names, whether I should mention that example or not. Where are the names? Yeah, Abdul, yeah. Anyway, some of you maybe, Abdul maybe will be interested in this example. Like you have an, let's see, infinite ring. infinite ring, commutative ring. And you want to know, what is the smallest number of ideals to select. Let's call it K. The smallest number of ideals you select from the ring, infinite commutative ring, so that we have R like 5, 4. What this mean? Here, I mean, I want 5 ideals where I1 is a strictly subset of I2, strictly subset of I5, or I have 4 ideals where Ki not K1 not equal Ki not equal Kn. Whenever you have I between 1, n less or equal 4, and I is not equal n. Okay? So what this mean, if you don't like ideals, you can do that for set. Like you select a subset of power set.
I'm not interested in that, Ayman. That question.
You are not. Okay, but yeah,
I'm
well, but
kidding
I
you,
thought
man.
this.
No,
Not interested.
It's a good question. It is a good question indeed.
Yeah, like how many items you should select in order to have a chain of 5 or thing. Yeah, so here the number will be still the same, like 3 times 4, 13. Okay.
We lost your screen.
Maybe now you can construct a formula for that. But let me give you another example, and then I stop. I can tell you the general result and just a little bit. Okay, here is the question maybe you want to ask. Go to the set of integers, positive integers. Okay, and let's select k numbers out of them. So I'm gonna select k, and I want R. Let's make a number here like 31, 21. What this mean? It means I want to have 31 numbers. I want to find the smallest positive integer I should select randomly, so I gonna, like, you're gonna select maybe 1,000,000. Maybe this is not the smallest. I mean, you know, I want to select k randomly. I want 31 numbers, let's say A1 up to A31, where A1 is a factor of A2, is a factor of A3, keep going, a factor of A31, or what? I want to have B1 up to B21, 21 numbers where BI is not a factor of BK, whereas I not equal K, and I and K are between 1 and 21. I mean, for me, this question, I mean, all of them, by the way, the number here is going to be 601. So what that mean? If you go and select 601 numbers randomly, you select 3, 7, 8, 9, 10, 15, 100, 205, 300. You select 601 numbers. Then you are sure there are at least 31 numbers where this is true, that, you know, I have the first number is a factor of the second, is the factor of the third. Yeah. Okay, what I'm trying to tell you, if your graph is partial order, and this is, by the way, this talk, if you want to know the details, this talk rely on a recent paper just appeared. Maybe some of you met my colleague, Rosie Risner. She visited me twice, and we work on this. In fact, it's funny. First, we were working on a problem has to do with the divisibility. And then we discover that we can generalize this problem to talk about partial order in general. Because divisibility, as you see, is a partial order give you on the set of integers or whatever. Anyway, if you want to know the details, this is a recent paper called Ramsey Number of Partial Order Graph and Implication in Ring Theory. If you are interested in this paper, I will be happy to send it to you. For this kind of a question, anybody can guess the formula? Remember that the formula for a graph in general is not known. The number we know is R1010, which is not precise. It's a number between 798 and 23,000 something. But if you can define a partial order on the graph, then you have a formula. Let me read the chat. Yes, that's the number. It's going to be n minus 1, m minus 1 plus 1. But remember, so that means if your graph is partially ordered, we know the Ramsey number. We have a formula for the Ramsey number in general. Okay. I think that's more than enough, and I really thank you for coming and celebrating with me my favorite day. By the way, I want to end up with telling you some stories about Paul Erdős. I think some of you know. Have you? I mean, you know what Paul Erdős? He's a Hungarian mathematician, and he's known for like the man who loved numbers. Or there is a book, The Man Who Only Loved Numbers. This person died in 1996, September 20, during what he does for living. He go from one university to another, just giving lectures, and he never held a university position. He like devoted 18 hours of a day just doing mathematics. And when you talk with Paul Erdős, you have to know his language. Like when he mentioned epsilon, he used the epsilon for a small child. He call him epsilon. If you hear him saying somebody died, like this person died, what he means with that he stopped doing mathematics. And when you hear his language saying like this person left, when he say that this person left, he means died. Okay, and usually he will tell somebody who get divorced, liberated. So you are liberated when you get divorced. So I'm not liberated yet. Anyway, it's interesting to hear. I mean, of course, I'm not saying his lifestyle is an ideal. I don't live that. I don't know. I mean, there is only one Paul Erdős I know. This person, he died, according to what I heard. What he owned will not even, like a briefcase. He has nothing. No house, no car. He just devote all his life doing mathematics. Yeah, I mean, I only know one Paul Erdős anyway. None of us is a Paul Erdős. Okay, and I thank you, and I think I stop here.
Thank you very much, Ayman. If you have any questions or comments, please let us know on the chat, or you can use the microphone.
Yeah, thank you, Amin. I am, yes, 25 years old. It feels wonderful. Can you tell I'm telling jokes, and I hope I understood your question. How does it feel to be 25 again? It feels wonderful. Thank you, Abdullah. And I thank my colleague. And in fact, I miss seeing you. Wallah, I miss. We used to at least, meet in the coffee room or on the stairs. Or I hope, like next, maybe. Is there any news we coming back or not really? Thank you, Ghada. Do you know if we are, Abdul, if we're gonna go back or?
No,
They said yeah.
no coming back this semester, not yet. But we supposedly coming back for the final exam. So definitely coming back, but I don't know when.
And what about, did you get the vaccine? Because I did. I took the first shot, and I think on the 25th, I will be doing the second one. What about you guys?
I took both, and that's why I think if the majority of the people will take both
So that's
vaccines,
why,
yeah.
So maybe that's why yesterday I talked to you, or the day before you told me I'm out of campus. So you have the courage to leave?
Yeah. But there are some side effects with the seminar today. You see it happen, something strange.
Yeah, Muhir, the whole seminar is funny story. You remember the first story? I mean, when I receive your email, I want to know the answer now. So I send it to the provost, because I don't want to wait for Jarrah or Arabtawi. I just want to know, is that, I mean, I could not believe it.
There are, I have a list of 9 documents to prepare. And I remember in the past, even for the local speakers, Nerissa asked me something. So I just wanted to ask her and have a reminder on what do I have to give her for a local. Yeah. And she replied, we still have to do,
for the local speakers who are from outside campus, we still have to do some of this stuff. For
the insiders, from the locals, like the ones from AUS.
No, we don't have to do that.
Yeah.
Anyway, that was when it's not, if it sounds too good to be true or too impossible to be true, it's very likely not true. That's typical, in life. There is always a probability of some certain probability that this is not the case, but most of the time, if something is too good to be true or too much to be true, then it's not true, and that was one of these cases. Anyway, it's okay.
Okay, thank you guys, and
thank you very much, Ayman. Very nice talk indeed. I like your examples, and it's very interesting. So you are saying you did this with Reisner?
Yes.
Is it published already, or is it?
Yeah, it is published. It's in fact in open access. It's in open math.
Which Which journal?
In fact, Open Math.
It's the journal is called Open Math.
Yes.
Yeah, I think either you sent us an email or I receive an email. I saw the paper one day, or I receive an alert from Google. I don't know.
Yeah, if you are interested, I send it to you, Abdul.
Yeah, sure.
If anybody,
sure. Yeah,
if anybody want to see this paper, two things: either send me an email. Oh, hi Sohail, but you are Sohail Khoury 3. Are you Sohail the one I know, or Isam, or because sometimes Isam enter with Sohail Khoury. Thank you, Sohail. I assume you are the real Sohail I know. There are two things if you want to know
from my laptop, from my mobile. You know, I'm seeing you from all over the place. You know, laptop, mobile, everywhere.
Okay, so like a student.
So no flowers, Ayman. We don't have flowers today.
No flowers, man. Even I told my kids, nobody tell me happy birthday, and they, you know, like they come and like whisper, and they are kind of shy. I mean, they don't believe that. I told them I hate birthday. Nobody tell me. Yeah. Anyway, thank you guys, and have a good day, and enjoy. Okay.
Yeah,
Bye-bye.
thank you all, and have a wonderful evening.